This is chapter 14. Just as we started the concepts of kinetics, we want to take a hypothetical reaction, reactants, produce products like that, and consider this diagram. In the introductions, we assumed the reactants had zero concentration before the reaction started. And we visualized this in terms of horses in the starting gate at a horse race. So the horses in the starting gate would be at point zero. It'd be 100% of reactants in the starting gate. Open the starting gate and allow the reaction to proceed to generate products. Well, by natural process, the concentration of reactant is going to decrease, and we know that the concentration of any products will increase. At a specific point in time, we find that the concentrations of the reactants and the concentrations of the product reach a point at which they do not change in concentration. So we'll choose this line for the moment and say that in the slope of tangent to any point in the line producing products, or a tangent to the line producing reactants, we find a non-zero slope. But when we get to this vertical line with, of course, accepting this artwork, the slope from this point, A, if you want to, on is zero. This marks the beginning of the equilibrium region. So we have, in general, identified anything beyond that vertical line as equilibrium. And have studied so far concepts from start of the reaction to this equilibrium point, and refer to that as the kinetics region. Issues in the kinetics region depend on a couple of issues that we've developed into the concepts. Factors affecting reaction rate. It's one of them, and you recall it's the can't see is the acronym that we gave you. It's still on the board here. Concentration effects. Surface area effects, effects. That's an N. The nature of the reacting chemicals. Temperature and energy. catalyst. From these, we construct what is referred to as rate laws. Which define empirically the generalized relationship and growth trends of the curve, or the rate changes of the reactants and products, whatever you're trying to study. And we learned what a rate law was for a general reaction. Well, over here in the equilibrium region, we want to look at a system which is in steady state change. In other words, it's not changing. Slope of time, concentration versus time, equals 0. So there is no factor associated with speed, acceleration, and it is a constant. Some people, constant change. Some people refer to this as a steady state condition, in which the reaction does not change concentrations as it produces products, nor does it change concentration as it produces product. Relationship between the kinetic region and equilibrium region is defined in terms of the law of mass action. The law of mass action stipulates that the rate of reaction in what we refer to as a forward direction is equal to the rate of reaction in the reverse condition. Consider this hypothetical empirical type reaction where A's, B's, and C's are substances, and lowercase a, b, c's, d's are coefficients. If we are examining the reaction from the A-B side to the C-D side, we have a rate constant forward, like that. It will be proceeding forward. If we're considering the CD side of the equation moving or going through reaction from right to left, in that time would be forward from right to left, if you would. we refer to this as the rate reverse, right here. At the equilibrium point in the curve that we showed you a moment, this is where this condition starts. This is the transition from the equilibrium region into the kinetic region, in which the rate forward in here is equal to the rate in reverse. Okay, with that in mind, we want to write a rate law, an empirical rate law, for the forward reaction in terms of A and B, and write an empirical rate law in terms of C and D, which define rates in their respective directions. When you recall, rate equals the rate constant times the concentration of the components raised to some x and y value. In the equilibrium region, the x and y value are the coefficients of the specified substance in a balanced equation. So for the forward reaction, we can simply write rate is equal to K forward times the concentration of A raised to the A power times the molar concentration of B raised to the B power. The reverse reaction is composed the same way. We have a rate equals reverse C raised to the C power and D raised to the D power. From this, we apply the law of mass action. Rate forward reaction equals rate reverse reaction, and substitute the expression for the forward reaction in place of the rate for the forward reaction, like this. Equals the expression for the reverse reaction as shown here. The next step is two options. We need to take this expression, rate forward equals rate expression reverse, and solve for a rate constant ratio such that as the reaction proceeds to the right, the ratio number increases. This gives us two options here. We want to solve for a ratio of rate constants, so I will solve for K forward over K reverse, and it will look like this. K forward, K reverse. And C raised to the C power times the concentration of D raised to the D power will be the numerator divided by concentration of A raised to the A power, again divided by the concentration of B raised to the B power. The central issue is write a ratio of rate constants, forward over reverse, or we can have the reciprocal of this, K reverse over K forward, to equal, flip this over, A raised to the A power, B raised to the B power, C times concentration of D power. Which of these should we choose to represent an increasing concentration of product numerically? Now, that may be an obscure comment. The comment was, choose one of these ratios that represents a reaction. Let me get the reaction back on the screen. Such that that would have an indication that the CD side is increasing. When we talk about ratios in a dynamic context, we're talking about changing the whatever number is in the numerator versus whatever number in the denominator. If the reaction is, now watch, this is the key. Watch what I do. Stop writing and listen. If the concentrations of C and D are increasing, you're proceeding left to right. I'll say that again so everybody can understand me. If the reaction is proceeding left to right, the forward indicated forward direction, then C and D are increasing. Everybody good? What are A and B doing? Decreasing. If we look down here, if C and D are increasing and A and B simultaneously are decreasing, this entire number will be going up or be large. But if we looked at this one and from a left-right context, if we take this one as the numerator, what from left to right is this doing? It's decreasing while that's increasing. And so this ratio is going down. Chemists all over the world and throughout history have chosen the ratio that reflects an increasing number. That's by design. An increasing number means we're producing more product relative to the reactant side. Everybody good on that? This one. So this is, so to speak, tossed as an indicator of the reaction proceeding to products. And the one that's chosen to define the equilibrium is the one which would represent an increasing product side from left to right. The ratio of the rate constants, now, listen to this is key, is redefined into what we call an equilibrium constant. and is represented by a capital K with a subscript EQ. And for any reaction being in an equilibrium condition, the equilibrium constant is equal to the product of the concentration of the, see, we got products up here, divided by the product of the concentration of reactants raised to their respective coefficient powers. So in this consideration for our hypothetical first reaction, we want the equilibrium constant for this reaction. We'd write the concentration of C times the concentration of D raised to the CD power divided by the concentration of A times the concentration of B raised to A and B power. And it would look like this.
That was the decreasing one.
Yeah. There. Sorry. So we have products over reactants. And as we typically want to read an equation, it generally says that the reaction, first of all, is proceeding left to right, producing products. What does this physically define relative to a chemical reaction? It defines extent of reaction. That says extent of reaction. Some reactions reach equilibrium very quickly, and some reactions do not. If we consider the growth curves for a couple of reactions, one that reaches equilibrium quickly and one that does not, over time, concentration, if a reaction takes a long time to reach equilibrium, say in this case, I'm hypothetically identifying this as the one that takes a long time. Right here. Versus a reaction which would take less time. Let me get out of something you can see. So the equilibrium region for the blue graph is reached sooner than the equilibrium region of the black graph, so to speak. The equilibrium T1 would produce a larger number than the T2 curve. Okay, it wouldn't have a very long time period, okay, to produce the concentration or reach the equilibrium points. It would, and I'm just exaggerating the graphs to illustrate the concept. When we start using real examples, it'll make more sense, hopefully. Because this shows a small number, versus this showing a large number. We identify certain reactions relative to their efficiency to deliver products. A reaction which would have a small K value does not deliver very much product. One with a large K value, as in T1 example, produces a large KEQ value. Units are not significant. The magnitude of the number is the issue of interest. If a K value is very, very small, low concentrations of product are present at equilibrium. If we're looking at a large KEQ, we're looking at, relative to the low one, higher concentrations of product at equilibrium. Now here are two reactions, ionic ionizable reactions. You notice both of them have a double arrow, which means they are already in the equilibrium condition. The rate of the forward reaction is now stabilized with the rate of the reverse reaction. On the very end down here, you will see where I've tried to write a KEQ, and the first number is 4.9 times 10 to the fourth. And in the second one, which I forgot to write the KEQ on, now I've got it right in there, it shows 1 times 10 to the minus 14. In case 1, it's a number that large, just from the number, says that that reaction, when it proceeds, will produce almost all products, and almost no reactants will remain in solution. Concentration of products is almost infinitely higher than the reactants. In the second case, the ionization of water into hydronium ions and hydroxide ions, as you see here, is infinitely small. This is approximately 10 to the minus 7, which is almost undetectable. So when we talk about using the K value in terms of describing a reaction, we use it to get a relative idea of its efficiency. Now you'll find these used in a number of cases, and what they do, and what is typically done in the literature, is the K value has a subscript that represents the character and nature of the reaction. Now this applies with a little discrepancy, but for the most part, as you go through this book, you'll find that the KEQ will be changed to a KC for gas phase reactions. Now, the K value does not tell you anything about the fact that it's a gas phase reaction. KC is used elsewhere also, but not nearly as much as it's used for gas phase reactions, especially in this textbook. If you are working with acids and bases, or acids, you will see that K value subscript with an A, and this will refer to the acid ionization constant. The larger Ka, listen to this, mark it down, the larger Ka will be the stronger acid. Here is a table of acid ionization constants for weak acids. Acetic acid, here's the formula. And that says 1.7 times 10 to the minus 5 if you can't see it from the cheap sheet. Next one, 6.3 times 10 to the minus, it looks like a 3. Actually, 10 to the minus 5 also. Then you have the next one, boric acid, first ionization would be 10 to the minus 10. How do we compare strength of first ionization of boric acid to either benzoic or acetic? Benzoic or acetic are stronger acids. They deliver more of their product, hydrogen, which characterizes acids into solution. If the K value has a B, it is a base ionization constant. There is a class of compounds called amines, which are ammonia derivatives, which when put into water coordinate with water and ionize at the hydroxide. Well, these are classified as weak bases. Here you see, and I'll hold the book up, here is ammonia when put into water will have an hydroxide ionization K, or base ionization constant, I should say, 1.8 times 10 to the minus 5. Aniline, which is a benzene ring with an OH attached to it, that's phenol, sorry. Aniline has a methyl group attached to it. Wrong again. It's an NH2 group attached to it. Aniline, when thrown into water, has a 10 to the minus 10. It is a weak base than the one with 10 to the minus 5. So what am I trying to tell you? There are many tables. These are salts that are put in water. Aluminum hydroxide. I doubt you can see these things. I apologize for that. Try to focus it a little better. Okay, this one has a 4.6 to 10 to the minus 33. Minus 10, minus 6. Here's a minus 26. 1839. There was one in here. It was a 50. Yeah. Here's one that's a minus 52 that's been determined. You can determine these numbers. Something that is a minus 52, 10 to the minus 52, maybe send one ion of sulfur and one ion of mercury out into solution. Very, very poor ionization. These are salts. Salts do ionize into solution, but some of them have very, very poor ionization characteristics. Some have almost infinite ionization. Sodium chloride is, you can put many, many pounds per gallon in thing. You can get up to 10 pounds fluid using, I think it's 10 pounds. Dissolving salt. Well, you take, on the other hand, if you try to dissolve silver chloride, you probably couldn't get it up to increase it by any more than an ounce at best. Couldn't get probably a fraction of that because silver chloride has such poor solubility. You can come in here and look. Silver, there it is. It has a 10 to the minus 10th ionization constant. These are called KSP numbers. And these refer to solubility product constants. And for the most part refer to salt ionization in water, like that. Other K values that are used to describe a process or reaction might be a KF, which is called a formation constant. Or KD, dissociation constant. As we go through each of these issues, you'll get used to the subscripts because the entire chapter will deal with that. But one common denominator for all of these is the size of the number. A large number means a lot of product in the process is produced. And a very, very small number means not much is produced. And of course, that is a relative issue. You have to have a comparative. We're talking about ionization of acids. If we want to try to compare acetic acid to hydrochloric acid is a strong acid and it ionizes 100%, so its K value is at 10 to the infinity. There's no molecules of strong acid. But acetic acid only ionizes about 1.2% at 25 degrees. Very low ionization count concentrations. 10 to the minus 5, I guess. Very, very low molarity. So this is, at this point in our discussion and presentation, I'm trying to tell you how equilibrium is defined, where it comes from, and how it's used in a big picture context. In essence, I'm saying this is what it means. You might want to jot these down. I'll give you some time. In working equilibrium problems, one of the first things you need to deal with, of course, is mass of reactant, mass of product. In the dynamics of getting to equilibrium, we can construct a simplistic table that can help us solve a given problem. And it goes, and when you're approaching an equilibrium problem, step one, write the equation down. And below that equation, construct a little box table, as I've shown you. And this last row is the equilibrium. we indicate that with a negative X. We don't know how fast it's going down, but we know it's going down, and the appropriate symbology in that kind of problem is put in a negative X. What are the products doing? Going up. Plus X, plus X. Note, if, hypothetically, if I had a 2 in the equation, I would have put a 2x here. If I had a 3, say I'd have put a 3x. It reflects the ratio of gain or loss. So this one would be 2.50 plus a minus x mole. This one would be x plus 0 mole. The last one would be x plus 0 mole. This was from the problem. Can you figure out what x is from that? And what did I say? Row 1 algebraically plus row 2 gives you the third row. If I've got x, I can fill in the row. And that's going to happen all the way through the textbook, just like that. So in this case, it's easy enough. 0 plus x is equal to 0.338 mole. So that means if x is 0.338, this one's going to be 0.33. With this information, knowing that x is that, how do we get the equilibrium amount of PCl5? Subtract it, right? Okay. So this would be 2.162 mole. And these two are specified at equilibrium. 1432 reads as follows. Nitrogen monoxide, NO, reacts with bromine to give nitrosyl bromide, NOBr, according to the reaction. A sample of 0.0524 mole of nitrogen monoxide. Along with 0.0262 mole of the bromine, gives an equilibrium mixture containing 0.0311 mole of the nitrosyl bromide. What is the composition of the mixture? As shown here. So you have to memorize that in context of the problems and know what. How much product do we have? Now watch this, and I'll ask this 100 times. You know the answer. How much product do we have here? It hasn't started yet, therefore we don't have product, right? So just enter a 0 there. They're still in the starting gate. assume the reagents will follow the same trends that you would expect in a 0 to equilibrium trend concentrations changes. And these are your reactants. Both of them will decrease in concentration. Okay? And your product side will increase in concentration. But since these have coefficients in them, you have to include those. Here, the reactant side is going down. So you start with nothing over here. You got to make something. So you know it's got to make it from here. So those are minus 2x. Notice how the 2 is used for the coefficient in that. We have an understood to be 1 here. So all we need in this row is simply an x. And product side, of course, is going to grow with time. And so we enter that right there. And so at equilibrium, we are looking at 0.0524 minus 2x as the equilibrium concentration of nitrogen monoxide. We're looking at 0.0262 minus x for the concentration equilibrium for bromine, and we've already given that one. Since the algebraic sum is equal to the equilibrium, then from here, 0, and I'm doing this for emphasis, 0 plus a plus 2x is equal to 0.0311 mole. Solving for x, 0.0311 divided by 2 mole. So in this case, that's a 5. Five, 6 mole. Of course, since that is x, we can simply apply it to the equations in the change blocks and compute the equilibrium amounts. So this one would be 0.0262 minus 0.0156. And this one would be 0.0524 minus 2 times 0.0156 to equal. Okay, so that should clarify that type of problem. We have 0 moles before the reaction starts. As the reaction proceeds through the kinetic region, it will decrease SO2 in an amount 2x, the coefficient. Oxygen will decrease 1x, and the SO3 will increase as a product by 2x, leaving us with calculation 0.0400 minus 2x, 0.0200 minus x, and they gave you that value right here. Well, from this expression right here, we can calculate x is equal to 2x is equal to this. Well, I better write it in. 2x equals 0.0296, which of course gives x to equal 0.0296 over 2, which equals 0.0148 mole. Now we apply that in the positions for the x in each equilibrium case. So this would be 0.02, and I'll leave the last minus 0.0148, and this comes out And then the last one is
I added another tray for you today.
part of this. Pretty straightforward, huh? Any questions that we need to address here? Nothing more, nothing less. Now the question is, how do you get the equilibrium constant here? The equilibrium constant is always in terms of molar concentrations. So for each of the equilibrium values, they must be converted to molar concentrations. That's why I gave, or had to give, the volume of the reaction flask. First thing we want to do is write the equilibrium constant expression. For any reaction, once you determine the direction of the reaction, that's left to right in this case. Now there will be some that will be reverse that, and you'll take the reciprocal of what I'm about to write. But this one goes left to right, and your Kc expression is a molar concentration of the products, or the product of the molar concentration of the products, divided by the product of the molar concentration of the reactants raised to their respective coefficient powers. Order of reaction is the coefficients. So this is written, of course that's a gas in the brackets, and raised to the second power, and oxygen gas right here. The third row in our table, the underlined orange portions are not in moles per liter, they're in moles. So each one of these must be converted to molarity by dividing by the 2. So the concentration of SO3, we have, I'll start there, 0.0296 mole in a 2-liter chamber gives us 0.0148 molar for the SO3. Moles over volume in liters. We'll just work our way backwards. Oxygen now is equal to 0.0052 mole in the same 2-liter flask, 0.0026 molar. And finally, the SO2 concentration is 0.0104 mole (0.0052 molar in the sulfur dioxide. Any questions? So for the SO3, (0.0148 molar. I'm not going to worry about the units. Why? Because K value is in essence a proportionality constant. Our interest is in the magnitude of the number, not the units. In a few places that we will cover, the units become important, but not here. The interest is primarily in the magnitude of the number that we get. Okay, it has to be raised to the second power. The denominator, SO2 now, is 0.0052. That 2 is squared based on the equation that we're using. And oxygen is 0.0026 molar to the first power. I get 3,116.